In this example, we're going to sketch the graph of a rational function, making sure that the behavior is correct at the zeros, wholes, and vertical asymptotes, as well as having correct end behavior. Now, this rational function is given in such a way that the polynomial on the top and the bottom is both an expanded form as well as factored form. And really, the factored form is the more useful form, because from the factored form, we can actually read off the information that we want. And so looking at this factored form, the first thing that I want to point out is there is a factor that is on the top and the bottom that we could reduce out. So that x plus 4 that appears on the top and the bottom, we could reduce this out. So one copy of the x plus 4 goes away, leaving us with one copy left on the top, but none on the bottom. And so the only factor on the bottom is the x minus 1. Now that equal sign only makes sense if you specify that x is not equal to negative 4. Now that negative 4 is coming from the fact that in our original rational function, we had the factor x plus 4 on the bottom. Now, had we plugged in negative 4 into that particular one, we would be dividing by 0, but we lose that information when we reduce it completely out of the bottom, and so we've got to keep the information by adding that domain restriction. So now that we've got our rational function in the lowest terms, we can read off much of what we want. I'm going to start with end behavior. It takes a little bit of work to get end behavior when it's in factored form. Same goes with polynomials. We're really looking at the ratio of the dominating terms here. So let's write that down. Ratio of dominating terms. For polynomials, we were looking at just the dominating terms, our highest power term. But here, a rational function is a polynomial over a polynomial, so it makes sense that it would be the ratio that we're looking at. And we can look at that ratio in the reduced form. So we've got for the top, we've got the highest power term in the first factor being our 2x, because we're taking away the plus 3. And for the second factor on the top, our highest power term is x, because we eliminate the plus 4. It's a lower power term. On the bottom, we have the x factor that we keep, because we take away the minus 1, because it's a lower power term. Now, when we reduce this, or when we multiply it out on the top, we'll do that first. We've got 2x squared on the top, and we've got x on the bottom. When we reduce that out, that would be just like a 2x. Now, a 2x is a polynomial. It's a line, and we know that the end behavior of that line would look like this. We're getting that from the fact that this is positive coefficient, and this is an odd power, just like that polynomial. So now we know what the end behavior is based on the ratio of the dominating terms. So the next thing we want to look at is zeros. So zeros would be anywhere the top is equal to 0 within the domain. So top equal to 0 in domain. And I have to specify in domain because when we're looking at the two factors that are on the top, one of those gives us a 0 that's not an actual 0 because it's not in the domain. So let's see how this plays out. Zeros are going to be where the top is equal to 0, so we'll set the two factors equal to 0 and solve. So that first factor, 2x plus 3 equal to 0, gives us x equals negative 3/2. If we subtract the 3 over, divide by 2, and that is in the domain. But this x plus 4, when we set that equal to 0, we get the x equals negative 4. This is not in the domain. But I'll tell you what this ends up being. This ends up being a whole because that's the piece of information we had to keep when the factor got reduced. The x cannot be equal to negative 4, even though in reduced form that's not so obvious. So this is actually our whole, so we've taken care of our whole here too. And see, that whole is somewhat behaving as a 0. It's just going to be a missing point there. So let's look at this behavior here. Each one of those factors in lowest terms had an odd multiplicity. And so for each one of those, we're going to have that it crosses. It just happens to cross at a hole there for x equals negative 4. So now we've taken care of in behavior, zeros, and along the way we also took care of our hole. But we also need to look at one more thing, vertical asymptotes. Okay, vertical asymptotes would be wherever the denominator remains equal to 0 after we've already reduced out this fraction. So we've got the factor x minus 1 on the bottom in our reduced form, and so that gives us the vertical asymptote x equals 1 when we solve it. Okay, so now we've got all the pieces of information and we want to be able to graph this. So let's move on to the next page here, and I've just put in the information so that we can put it all together in our graph. Let's see, zeros, we've got x equals negative 3/2, and we've got a hole at negative 4, 0. So let's mark those two places, negative 3/2 and negative 4. We know there's a hole at negative 4, 0, and we know that there is an actual root there at negative 3/2, a 0 there. So we know that point's in there. We also know that there's a vertical asymptote at x equals 1, so we'll go ahead and put that vertical asymptote in there. That's going to be at x equals 1, and we know the end behavior starts down here and ends up here. Okay? So once we have that piece of information, all of those pieces of information on our graph, we need to just piece together what's happening here. So I'm going to work from the left to the right, just like we did for polynomials. I'm going to start here at this this left arrow, and I'm going to go towards my first interesting thing that happens, which is my hole. Now that hole is acting like a 0 because it remained in its reduced form, but it just happened to not be in the domain. And we decided that since in reduced form that factor had odd multiplicity, we were going to go through the x-axis there at that hole. So we continue on. But then we need to make sure that we're coming back down to the next 0, the only 0 that we have, and we're supposed to cross at that 0 as well. So we cross there. So now the next interesting thing that happens is this vertical asymptote at 1. Now we have to remain below the x-axis the whole time we're approaching that vertical asymptote, because there aren't any more zeros and there aren't any more discontinuities. So we're going to continue on here, and we're going to realize that our vertical asymptote, as we approach it from the left, we're going down to negative infinity. Now, taking a look at what's happening on the right-hand side of the vertical asymptote, we have this upward arrow here. And so I'm going to kind of deviate from the moving from left to right so that I can get this final piece in. There aren't any more discontinuities or zeros between negative 1 and infinity, so I have to stay up here above the x-axis because that's where my end arrow is. So I must be doing some sort of like little dip down here and then approaching the vertical asymptote as we come in from the right going up to positive infinity. And I will tell you, because that vertical asymptote came from a factor that had multiplicity 1, we would expect the arrows to be going in opposite directions, so that makes sense as well.